some things that we kind of picked up with from yesterday's lecture. Where are we heading? Where are we going? That type of thing. We're talking about reactions that occur on benzene rings, and that's this stuff in the bottom left-hand corner here, saying, whoa, that exploded. Saying here's a set of reactions that occur on benzene rings, of which some of these reactions will instill something in red here, which is our electrophile, onto that benzene ring, and other reactions will change the thing that's already attached on the benzene ring. It'll somehow modify what's there, and so maybe we convert from an O2 into an NH2 through a reduction type process. Maybe we substitute hydrogens out in place of bromines, or maybe we oxidize completely that carbon atom. So some other options of things that may occur to these reactions. And what I really want to start to say is let's take a look at a story of really Alfred Nobel, and how I can tell this fantastic story in lieu of or rather with the chemistry that we've been learning together. I'm a chemist, and I have benzene. And the first reaction that I conduct on this benzene molecule is to Friedel-Crafts, and this would be the reaction right here in red, and acknowledging that you could absolutely switch out any R group here with some rearrangement considerations when using Friedel-Crafts alkylation. But regardless, I can instill a R group, in this case, a methyl group, on the top of that ring, or really anywhere on that ring. It's arbitrary. Then what happens is I could add sulfuric acid and nitric acid together, and that should react with this monosubstituted benzene ring. And then the consideration becomes, if I have something already attached to this molecule, to that benzene ring, where is it going to direct the incoming thing? And also remembering that when you see any one of these reagents right here, when looking at these electrophilic aromatic substitution reactions, it becomes important to identify where is the electrophile, because when you do, and Abby, this is something that you mentioned in your question that we kind of addressed in the Q&A last night. Once you're able to identify what that electrophile is, then the reaction mechanism is going to be the exact same for every single one of these reactions. And so if this, then you should expect the same. If we acknowledge that this NO2 has a plus charge on it, that becomes a very evident, I'm redrawing a plus charge next to a plus charge, but in green, I'm hoping to relay the idea that this is again an electrophile that'll become very easy for us to utilize, and a very good one. Great. And so we should expect that to react in a similar fashion as we would this decent electrophile here. And so owning that those things will absolutely react in a similar fashion, we then have to ask the question of where would this sucker direct that? And so if we're just going to add an NO2, where would this direct? And I've given you a set of rules that begins with saying, does the atom directly attached to the ring have a lone pair of electrons? And this is kind of your thought tree that you have to progress down. And when we look at this reaction, here's a really comprehensive set of substituents that could be attached to a benzene ring, owning that the left side of this portion here are all things that could potentially activate the benzene ring, while all the things to the right here are things that could deactivate the benzene ring. And again, the shortcut to identifying these types of things are saying, and there is an exception, but generally saying if the atom attached to the benzene ring has a lone pair attached to it, then by all means we would expect it to donate electron density to that ring and be an activator. And we see that's true for all of these substituents. And here's an R group. And there is obviously not a lone pair of electrons on that carbon atom, but rather than memorizing every single one of these potential substituents, if you just remember that in R group, any carbon atom is just going to slightly add some electron density inductively through that sigma bond, then you would acknowledge that, hey, those are activating, and this substituent is expected to direct to any one of those three places. And so, again, here's that chart. And just before I continue with this problem, don't forget that these activating substituents should direct orthopara, and so we should expect those things to direct to these spaces. And don't forget the halogens here. They happen to be weakly deactivating, yet still orthopara directing. And just acknowledge that as well as the other exception. Moving back to the problem, then the actual product that we would anticipate to have in this solution as the major product, that is not correct. We're adding a nitro group here. And Dallas, I think you might have asked this question yesterday during lecture as well. We certainly would anticipate to have some amount of the ortho substituted product as well, but we're looking at the major product, and based on sterics, we would anticipate that nitro group to install itself at that position. It turns out that this nitration reaction kind of runs amok very quickly because it's really hard to control the stoichiometry of something that you're generating in solution. And so it turns out that we have an excess amount of NO2 around, and what happens is we have to ask the question of, well, if there's excess electrophile around, where does the next electrophile go? And so we'll ask the question of, the things that are already attached, where do they direct? And this methyl group is likely to direct at these positions, of which this is no longer an option. There's a nitro group there. And don't forget, implicit hydrogen here, but once the nitro group has been added, that hydrogen is gone. And that is a fundamental mistake that I made. I always thought there was a hydrogen here, and so that space was open again. And if you're just like, God, I can't believe this professor is teaching my class if he made such a stupid mistake, because that would be a carbon attached to 5 things. That's just where I was. And so I can certainly understand that those types of misconceptions can happen. Don't make that mistake. Again, it's one of my patented mistakes that you can't use. When we look then at the other portion of this molecule, this NO2 group, that NO2 group is, it falls in this chart. It does not have a lone pair of electrons on it. It is absolutely a full-fledged positive in one of its resonance structures. And so it is incredibly strongly deactivating. And so we would expect this species to direct to the orthometa positions right here. And so we have agreement between these two different substituents on where the next nitro group should go. They both seem to be in agreement that the next nitro group will instill itself ortho to the CH3 group, or it will occur meta to the already existing NO2 group. There's no real nice way of explaining precisely where that is. You have to kind of say where it is in with respect to its reference point. If we were to continue at this rate, then, and it does continue at this rate, and believe me, believe you me, it does. yoink, HNO3. Again, there's another possible installation of nitric acid and sulfuric acid, the nitronium ion, the NO2 thing. There's another possibility of installation of that NO2 group onto this ring. And so we again have to go through this series of questions of saying, if we could possibly add another electrophile, where does it go? And hopefully in this exercise, you've seen that I've never once asked about the nature of the nitric acid being added, or the nitronium ion being added. That has nothing to do. It is completely independent of state what it is. The where it's going to go, the electrophile, where it's going to add on that ring is completely independent of the electrophile itself. No matter what this sucker is here, it is likely to add right here every single time in its major product. And so when asking questions about where does this nitric acid, sulfuric acid, nitronium ion product of that mixture go on this ring, it has nothing to do with this right here. And that was something I thought. It has, where this is going to go has everything to do with what is already attached. And the CH3 thing is again directing to these positions right here, of which two of them are already occupied. This NO2 group that was distilled on the bottom of the molecule, it's directing to these positions on that benzene ring, of which of one of those positions is already being occupied. And then I'll try and use running out of distinct colors. We'll put a triangle above this NO2 here, saying that is also going to direct to this position right here, and it wants to direct to this position, meta, to that nitro group right here. And all of them seem to be directing to this remaining position that is ortho to this methyl group. And so the final product of this reaction features first the installation of that methyl group, which makes this molecule called toluene, and then that toluene gets sequentially nitrated to form this molecule as your end product, and you have tri-nitro toluene, or TNT, one of the most explosive molecules known to man. And if you're Alfred Nobel and you synthesize this molecule, you are so, apparently, as legend goes, you are so absolutely horrified by what you perceive to be the massive amount of destruction and death that this molecule that you just invented could bring to the world, that you create a number of different prizes that you and I know as the Nobel Prizes to award people and for humanitarian, medical, and scientific advancements in almost all fields except mathematics. I believe that's the Fields Medal. And I think the rest of these other disciplines all have some type of Nobel Prize, and it awards these people the profit that he made off the sale of TNT became the award prize for the Nobel Prize. I think you win $1 million if you are awarded the Nobel Prize. And so chemistry right here having a major impact on life, period, moving forward. And so that's the story of TNT. There's a great book, I think it's called 20 Molecules That Changed the World, and they're just these brief little vignettes about how just, and this is ultimately why I'm a chemist, is how one molecule could absolutely just make such a huge impact on the entire world. Look at TNT. It's just absolutely fascinating. And if you're really, really hard pressed for a molecule that's absolutely changed the world, it's water. And so that's my favorite molecule, period. And so it's just fundamentally, I've always been interested in how molecules can have a huge impact on people's lives. Here's how someone took the award winnings, the profit from what they made and turned it into good. And so that's the story of TNT. More importantly, what your task will eventually become when looking at these types of reactions is saying you're going to see something that looks like this, which is simply saying if you were to start with benzene, and let me make sure to do this correctly with an with a good example here. Could I synthesize this molecule? And on your examination, you're going to be tasked with this exact thing. Can I develop a series of tests, steps, synthetic steps, that allow me to start with this molecule and undergo a series of reactions? Maybe I add this first, and then I add this next, and I make this third. It's kind of syncing together sequentially these reactions and accepting and understanding the implications of direction. Can I start with this molecule and eventually make this? This is a orange, Clemson orange. This is a synthetic arrow. And this is just shorthand, again, for saying, starting with this, make this. And I'll just write ... through a series of sequential synthetic steps. And this is ultimately what makes organic chemists so incredibly crucial. If let's say as a computer scientist you identify and model this really cool receptor that is for, let's say, something like ALS. And there's a receptor in the body that is a really promising target. And if we could make a molecule that could fit into this really cool pocket of this receptor, perhaps we could prevent that receptor from binding to some, oh God, we're going to have to go in some biochem and biology here, but that receptor prevents an enzyme from binding and catalyzing some type of reaction. Oh, we're back out of there. Then if we could make this molecule and prevent that enzyme from binding, then perhaps we can arrest some type of processes and maybe improve some symptom, or maybe even alleviate or remedy the disease. And so that's the idea of rational drug design. And maybe this molecular modeler said, hey, if you could make something that looks like this, that's got this halogen over here that could fit in this pocket, and then something that's got some hydrogen bonding capability here, great, and the molecule needs to be completely flat to kind of fit in there like a key, then we're in really good shape. How can we make this? And then the synthetic chemist goes, oh, okay, not only do I have to figure out a way to do that, I need to figure out a way to do it efficiently, and as efficiently, like in terms of fewest number of steps, and making sure that I make as much of the product as possible, making sure that I make a pathway that certainly diminishes the synthesis of side products, because if there's a side product to this reaction, I got to prove through FDA that it doesn't kill anyone. And so there's a lot wrapped up there in designing this drug. And so the first thing a synthetic organic chemist would do, and I have students that are working at Pfizer right now, and I think he's getting paid, just finished his grad school, just got his PhD, is getting like $95,000 right now to synthesize, go through exercises like this. It's fantastic. The question becomes, how do I make this thing? And so the first question I ask is, how do I install the stuff that is attached? And I've been using the word substituents here. And so simply asking some sub-questions of, can I start with benzene and add an NH2 group to that benzene ring? And if you look at the chart over here, here's a benzene ring and here's an NH2, an amine. This molecule is called aniline. And just some notes, not directly. it sure seems like I have to first add H2SO4 and nitric acid, and then reduce that nitro group to install an NH2. It's a two-step process, so something to think about. And it seems like I could directly install the chlorine atom by simply adding Cl2 and AlCl3. And so that kind of gets through just the brief exercise of saying, okay, at some point in time, I'm going to need to add an NH2. How am I going to need to do that? It appears like I need to add sulfuric acid and nitric acid first, and then follow that by some reductive process to make the NH2 from the NO2. And then over here, it looks like I can instill that chlorine in some fashion, and I can instill that chlorine, and it turns out that's direct. It doesn't require two steps. I can do that all at once. Thank goodness. We like things that allow us to do it all at once, and so we know how to do that. And so now the question becomes, which one should I install first? And if which installation. And again, so let me just take a quick second to time out here. Okay, why does every med school want you to take organic chemistry if you're really never going to use the organic chemistry ever again? This is the thought process of being a doctor. I'm a doctor. And the thing I practice on is organic molecules. You're going to be a doctor, and the thing you're going to practice on are human beings. And so your job is a little bit more higher stakes than my job, but the process by which we're going to go through the job is very similar. You have a patient that needs a certain set of therapies that need to address the disease that they have, as well as the some of the other things that happen to them as well. I can't think of what that's called. There's an obvious word for that. But the idea being that perhaps if you have to give certain medications, that you don't give medications that are going to conflict with one another. You know what you need to do, but there's certain steps that you need to figure out how they're going to happen. And it becomes your job to figure out the best way to assemble that therapy. And so yeah, it's OChem. I get that. And it's your fault for taking this course. That's why we're doing this today in the middle of summer. But in all honesty, there is so much to draw from organic chemistry in the practice and implementation in the medical field that'll become important to you later. You're just going to be playing at the lower stakes where B- students like myself play with molecules. But don't forget that this is absolutely applicable. And I think it's more applicable than most of the biology courses that are required for med school, because those are so much more raw memorization type courses. And that's not a knock against them, but the skill set that's required to get through a synthesis problem like this is very similar to the skill set you'll need to use when you're a dentist, a animal doctor, a human doctor. All of those different types of things are going to require this skill set, and I'm not sure you get it in a whole lot of other classes, and this is a great time to practice. I want to make this molecule here. Let's say that the investors that I work with have found some customers that we could make, maybe $100,000 per kilo on the synthesis of this. And so that's something that's really enticing to us. And it is. They're starting to build me a multi-million-dollar laboratory to do this science. And so how would I do this? Well, now that I know what I'm building here, the question then becomes, what's the best way to assemble it? And if I look first at I'll say then what? The idea being, if I installed the chlorine first, acknowledging that it is deactivating, but because it does still have these lone pairs of electrons on it, it fits Dr. Shaw's weird definition of saying that this sucker should, we would anticipate it to be weakly orthopara directly. So we would expect something to install there. Let's just keep moving on. Here's the NH2. And that NH2 does in fact also have a it does in fact have a lone pair of electrons on it, and we would anticipate it to activate the ring as a result. And as it activates that ring, we would expect it to direct the incoming electrophile to the ortho or para positions. And so now that I've kind of analyzed these two scenarios, the idea would be if adding chlorine first, if I were to have to then add the nitric acid, sulfuric acid mixture, I would likely anticipate producing this product, which is the para-substituted product, which I could then convert into the NH2, but that does not instill the NO2 group, which would then be reduced, but it'd still be in the same place. That doesn't get us to where we want. This is a different regioisomer, not stereoisomer, Dallas, regioisomer of this product right here, and so that doesn't get me along the path that I want. And if I were to start with the NH2 and then add the chlorine, AlCl3, well, that's not very helpful, because if I were to start with the nitration and then add the reduction to the amine and then try and add the chlorine, we're kind of stuck again at producing the regioisomer that we don't want. And so it becomes a question of saying, how do I add one of these two things meta to the other? Is there a way that I could potentially do that? And it seems like both of these pathways lead to the wrong stereoisomer, or I just did it, Dallas. That's not what I should say. The wrong regioisomer. Then is there a way to actually make these from using these steps you already have? And if you're looking at this and saying, yeah, there's one step that hasn't been talked about, which is the fact that there is still one more step here that we would have to do, or that the lead-in step to this reaction, or there is in fact a lead-in step to this reaction. Perhaps if we were to closely analyze the impact of what these other steps are, could we perhaps instill something? And the idea being that if what preceded this molecule here had to have been the nitro compound, and I'm wondering if we could perhaps utilize the directing nature of the nitro group and then do some of this chemistry selectively if we could get the regioisomer that we want. And so, again, the process is saying, I know what I want to make. I've got the tools that I can to make it. Now it needs to, now the sequence by which I make these, put these steps that I need to in place matter. Here's one possible way to do it. Oh, that doesn't work. Here's another possible way to do it. Nope, that doesn't work. Now I need to dig a little bit deeper and ask myself, is there other opportunity here that I could take advantage of? And there is. Let's take a look. If I start with this benzene molecule, all right, and if I were to add to that first H2SO4 and nitric acid, I would anticipate installing an NO2 group to this molecule at some point in time. Now, what's really nice about this part is if I look at this NO2 group, it is incredibly deactivating. And I would expect to instill that NO2, or the incoming electrophile, at the meta positions, which is really great for us because, hey, I want the regioisomer that places these two substituents meta to one another. Well, that's great. I guess the next thing to do then is add the chlorine atom next. And we're looking at the correct regiochemistry for two substituents about that benzene ring, of which we just have to simply change the chemistry of one of the substituents, and we will convert it into the correct NH2 that has been installed almost through magic in the correct position to that Cl. And it appears that we can't just use the two reactions that we need. We're going to have to take a look at utilizing this one at the right time in order to generate the product that we have. And most chemists that would go through this would, trying to make this molecule in an industrial setting might come through back and say, hey, there's no way we can do it. And the chemist that actually is worth their money will come back with the synthesis that allows for the installation of these things in the correct fashion so that this molecule could be synthesized. Let me just go through one more example of something like this, because this is really the meat of this unit, is being able to say, let's assemble the things that we know in a logical manner to make molecules of interest. Let me get an example from the textbook. I could make one up right now, but if I were, we could go down a rabbit hole here. Let me just find a really good example here. All right, so starting with this anisole molecule, which is the name of this CH3 attached molecule, could I synthesize this right here? And so again, we're looking at if I'm starting with this molecule OCH3, how will I need to instill the bromine? Well, I will need to instill the bromine onto the benzene ring by using Br2 and FeBr3. And those are the conditions that'll allow me to add a bromine group. And so that's good. Just reviewing these reactions here. Yeah, I could certainly add this acetate group onto the molecule using these conditions. So I have some sets of conditions that I could in fact use, and it becomes a question now of saying, and I'll just a phantom write this because we'll also have to consider this substituent at some point in time, asking ourselves what is the directing nature of these substituents so that we can determine what is the best order for us to assemble these reactions in order to achieve the product at the other side of this synthetic arrow. And so here's another time we can say, hey, here's the OCH3 that's already attached. That oxygen has a lone pair of electrons directly attached to that ring, and so I would anticipate the directing nature of this OCH3 is going to direct whatever comes next to these positions right here. And let's just walk through that then for some of these other examples. Here's the BR. BR we know to be orthoparadirecting, even though it is slightly deactivating. Orthoparadirecting suggests we should anticipate directing nature of that substituent to be ortho and para. And we can go through this again then too with our carbonyl ketone-based group over here, and acknowledging that this carbon that's directly attached does not have a lone pair of electrons directly attached to it, and as a result, we would expect that this would direct to the meta positions. That's not the meta position, that is right there. And so we have identified the reactions that exist. And so once we've identified the reactions that we could eventually use, it becomes assembling those in a pretty straightforward manner. If we were to start with this anisole molecule, it appears to me that that I could add this ketone group to this molecule, and it would appear to instill itself para to that OCH3 position, and so we could actively do that. I would expect to add this molecule or that group to the para positions, and here's a situation that you hope to stumble into in the examination, because through analysis the activating substituent is directing to this position, the deactivating substituent is also directing to the same, and so we have agreement, and so addition of the bromine we would end up with the product that we want in a fairly straightforward fashion. Sidebar. What about this scenario, though? Here we have a problem because this OCH3 directs to the ortho and para positions, and we no longer have agreement within the molecule on where we would expect to add the incoming electrophile. And at this part, we always have to remember, because activators add electron density to the ring, making it more negative, which is the same as saying more nucleophilic, ortho-para activators always win. Remember that we're still going to react negative charges with positive charges, and when we react those negative charges with positive charges, the stronger the negative and the stronger the positive, the more that they're able to attract one another. And so because this orange OCH3 is an activator, it will add electron density to these positions, making them more negative, and so any incoming electrophile is going to be more drawn to those positions, and as a result, we would only expect to see as the major product bromination occurring at Br and there would be absolutely no way that I would expect you to differentiate between those two products being the major, but certainly owning that this position right here would be sterically hindered, so that would absolutely lead to the minor product. This really wraps up the content for the electrophilic aromatic substitution portion of this unit. And so what I want to do is we'll take a break until the top of the hour, and then we're going to come back and talk about reactions of things with alcohol.
Hey, Doc, I got a quick question for you.
Go ahead.
So on the first example, we installed that would have been the Friel-Crafts alkylation, installed the CH3, and then it was an ortho-para director. I was having a little trouble logging in. That's because carbon is a electron donating group, like alkyl groups.
Mm-hmm. Yep.
Okay. Was just looking to relate that back and see why that was. And
it does not fit your rule, Dallas. And so, well, my rule, not your rule.
Yeah.
The one I'm forcing you to learn. It does not have that beautiful lone pair of electrons on it to make it obvious that it's going to be an activator. But yeah, it just is slightly activating.
Okay, and then so I was just like, I know it's not gonna happen, but with like the situation we just did, say you added bromine and you were testing through it, with something that's not as sterically hindered as that carbonyl group, we would still see a predomination of the para addition rather than ortho, just because of that minor steric.
Yeah, okay. It seems like it's not that much when you look on it on paper, but to an incoming atom, that's a whole lot of stuff to navigate.
Okay, awesome. Thank you.
Yep, we'll see you in a few.
We'll do.